All right, here are the notes for section 11.3, more on limits. So define the limit informally. So when we write the limit as x approaches a of f of x equals L, we mean that f of x gets arbitrarily close to L as x gets arbitrarily close, but not equal to a. So here, find the limit of x approaches 1 of x cubed minus 1 over x minus 1. So we can do this a couple ways. You can just look at the graph. So we'll graph our equation. X cubed minus 1 over x minus 1. Draw. So there's a curve. Let's reset the view window. There we go. So if I trace, you can see as x gets closer to 1. So if you notice, I get an, whoops, can't see it, you get an error. But there's 2.71 and there's 3.31. So it's probably going to get pretty close to, we can say it's 3. Or we can work out the algebra. That numerator is factorable. Limit as x approaches 1. That's x minus 1 times x squared plus x plus 1 all over x minus 1. So the x minus 1's cancel. Limit as, whoops, x approaches 1. X squared plus x plus 1, which becomes 1 squared plus 1, or 3. Same way. You could also do a table. You could do, so you'd work closer to 1. So essentially what you look at that is you do x, and you do f of x. So we're looking for, whoops, not 1, looking for 1. So I would do 0.9, 0.99, 0.999, and I also do 1.1, so differ by a tenth, by a hundredth, by a thousandth, and I would look and see the pattern of these values. So what number do they get closer to? Do these numbers approach some given number as I move towards, actually that's a bad example. These numbers should be in the opposite order. Should be, this one should be down here. These two need to trade. Because this one is actually closer to 1. So thousandth, hundredth, tenth, thousandth, hundredth, tenth. Okay, properties of limits. So sum rule. You've got two separate equations. You can break them apart and do their limits separately. Same thing for difference. For product, you can factor them. Constant multiplier, you can factor a constant term out. Quotient rule, provided that the bottom limit's not 0. Power rule, doesn't matter when you do the exponent. You can either do your power first and then take the limit, or do the limit first, then raise your power. Root rule is similar. So for n greater than 2, provided that blah, 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 are real numbers, that you can actually do the derivative, or the limit, I mean. Okay, example 10, the limit of sine x over x is 1, uses fact along with the limit properties to find the following limits. Okay, so we can break this guy apart. Would become x over x plus sine x over x, which can become, I can break it into two separate limits. So you have this, well, this is just 1, so the limit as x approaches 0 of 1, plus the limit as x approaches 0 of sine x over x. Well, up here it tells us that this is also 1. Oops, 1. Oops, so that's just 1. There's no place to plug in here, so this whole thing just becomes 2. All right, so 1 minus the cosine squared over x squared. Well, 1 minus the cosine squared is the sine squared. So this is the sine of x squared over x squared, which is the same thing as sine of x over x times the sine of x by x, which you can break into two limits. Limit as x approaches 0 of sine x over x times the limit as x approaches 0 of sine x over x. Well, those are both 1, so 1 times 1 equals 1. All right, so down here we got cube root. So both these things are the cube roots, so I can rewrite this as the limit as x approaches 0 of the cube root of sine x over x. Well, I can actually do my root after I take the limit, which gives me this, which gives me the cube root of 1, which is just 1. Okay, limits of continuous functions. So find the limits. E to the x minus tan x over cosine squared x. Okay, so let's see here. So what we're going to do is we're going to break this guy into chunks. So we can do all the parts of the limit separately. So the limit as x approaches 0 of e to the x minus the limit as x approaches 0 tangent of x all over the limit x equals 0 of the cosine squared of x. So this becomes e to the 0th minus the tangent of 0 all over the cosine of 0 squared. Well, e to the 0 is 1. The tangent of 0 is 0. Cosine of 0 is 1. Squared is 1. So this just becomes all just 1. So down here, we can do a similar thing. So the limit as x approaches 16 of the square root of n over limit as x approaches 16 of log base 2 of n. So this becomes the square root of 16 over log base 2 of 16. Well, that's 4. That's 4. So the whole thing is just 1 again. So you can always just work it piecewise. All right, so one-side, two-sided limits. So as the limit of f of x approaches c from the left is the left-hand limit. As approach from the right is right-hand limit. These are denoted with negative and positive. So c negative means as you approach from the left. Positive means you approach from the right. So it's the right hand and the left hand. Okay, so example 4. Find limit as x approaches 2 from the left and 2 from the right, where this is true. So this is my equation for less than 2. So if I approach from the left, I have to use this equation. So limit x approaches 2 from the left of negative x squared plus 4x plus, minus 1 becomes negative 2 squared plus 4 times 2 minus 1. So that is negative 4 plus 8 minus 1. So that's just going to be 3. Now, if I approach from the right, I have to use the other equation that's good to the right. So that's just this guy of 2x minus 3. So that becomes 2 times 2 minus 3. 4 minus 3 is 1. So the limits are different on either side, which means these functions don't meet up with each other. This is broken. All right, one-side and two-sided limits. A function f of x has a limit as x approaches c if and only if the left-hand and right-hand limits at c exist and are equal. That is, the limit as x approaches c equals L, if and only if the left-hand limits equal L and the right-hand limits equal L. So let blah, 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 find the limit as x approaches 3 and prove that f is discontinuous at x equals 3. Okay, so let's see. The limit as x approaches 3 of x squared minus 9 over x minus 3. That would become x plus 3, x minus 3 over x minus 3. So cancels. So this is the same thing as the limit as x approaches 3 of x plus 3. So this equals 3 plus 3 or 6, which the limit approaches 6, but the function has a value of 2, which means there's a break in the graph here. So there's an open circle at 6 or the closed dot at 2. So this function is discontinuous. I would have to pick my pen up in order to draw it. Okay, example 6, let intx, the greatest integer function, find as you approach 3 from the left. So this would be 2, because you would round it down. 3 from the right would be numbers more than 3, which the greatest integer function rounds down to 3. So here, as x approaches 3, does not exist. These the two one-handed limits are not the same thing. The limit does not exist. Okay, limits involving infinity. So in some cases, your functions can get very large or very small. So let's see here. But f of x equals sine x over x, find the two limits. So we need the limit as x approaches infinity sine x over x, and we need the limit as x approaches negative infinity of sine x over x. Now, so here's the thing. Sine never gets bigger than 1. So if you think about this, you can't actually, there's no algebra way to do it. You just have to use your finger to look at the graph. This never gets more than 1. This is getting very, very large, so this whole thing's going to be 0. The same thing's going to happen over here. If the bottom of the fraction gets super large, the whole fraction becomes 0. And if you look at the graph, sine x over x, we'll zoom out a little bit. So x approaching infinity means you're going off the graph to the right. Oh, it's kind of out of focus. There we go. Almost had it. Anyway, it's getting really close to 0 as you go off to either side. So positive infinity is off to the right, negative infinity is off to the left. All right, let f of x equals x e to the negative x. Find the two limits. So the limit as x approaches infinity of x e to the negative x, which is the same thing as x over e to the x. Negative exponents sit on the bottom. Same thing's true over here as you approach negative infinity. All right, so if x is infinity, this is going to grow much larger, much quicker than that. So if you look at the graph, the first one becomes 0. Over here, though, if I make e have a negative exponent, it's going to move it up to the top. So it's a very infinite number. That's a negative number. So this is going to be negative infinity. If you look at the graph, let's see if we get the graph to show up. X e to the negative x, draw. So you see there, as I go off the left, it goes down to 0, or negative infinity. So as x approaches negative infinity, the y value goes to negative infinity. But as x approaches positive infinity, the value goes to 0. You can also do tables for infinite limits. Like if you want to do the limit as you approach positive infinity, you want to pick x values like 10, 100, 1,000, 10,000. If you want to do negative infinity, you would do negative 10, negative 100, negative 1,000, negative 10,000, and see what these y values approach, if anything. If they keep getting larger or smaller, or keep getting larger, then you have infinities. All right, find the limit of x approaches 2. So we're looking at this guy. 1 over x minus 2 squared. So we can't just do substitution, because if I plug 2 in, this becomes 2 minus 2 is 0, 0 squared, which gives me 1 divided by 0, which you cannot evaluate. But 1 divided by 0, whereas it doesn't have a number, is infinite. Because as the bottom of a fraction gets smaller, the whole fraction gets larger. Once again, if you look at the graph, as you approach 2, the graph will spike. 1 over, oops. Whoops. So there's your graph. If you notice, there's big spikes going to positive infinity as x is close to 2. All right, last example. Find the limits. So this one, once again, we're looking at the graph. Sin x over x. So I can't do substitution because I would get 0 divided by 0, which I can't evaluate. But if I graph sin x over x, there's my shape. If I zoom in, whoops. You can see as x approaches 0, the y value approaches 1, and that's what the limit is. You could also do a table. So if I want to do the table, I want to approach 0. So 0.001, 0.01, 0.1. So there's moving. And then down here it'd have negative 0.001, negative 0.01, negative 0.1. So these are getting closer to 0 from either side. So in general, when you're setting up a table to do this, if you want to do the table to do the limit, you set your a value in the center, what your limit's approaching. this is a plus 0.001, a plus 0.01, a plus 0.1. Going down, it's minus 0.001, a minus 0.01, a minus 0.1. And then you're looking at, as you come towards A, do these numbers look like they approach a given value? But that is the end of the section.